what we have in the case of working with second order non-homogeneous differential equations, and I'm going to start out with cases where you're not going to have any duplication of any of the complementary roots. And let's say, for instance, we have looking at solving for y of x. Here we have a second order differential equation whereupon we have y double prime plus 4y prime plus 3y is equal to x times e to the 4x minus 7. And again, if we're looking at solving for y of x, once again we're looking at both the particular and complementary solutions. And just starting out again, if you're looking for the complementary solution, this would be if you were setting what we have on the left hand side of the equation equal to 0. That is, if you were to make this equation homogeneous. And so we have translating to what we have along the lines of the characteristic root equation. So y double prime we have, again, related to r squared, 4 times the first order derivative. We have runs parallel to 4 times r, and we have a 3y. That is going to translate to just the constant 3 since there's no order in the derivative. And looking at factoring, again, so we have the quantity of r plus 3 times that of r plus 1 is equal to 0. And it does not matter how you order the roots. But if you have r plus 3, and let this be the source from which we're going to have our first resulting root. So we have, in this case, we have r sub 1 is equal to negative 3, and if we have the second root to steal from isolating r plus 1 and setting equal to 0, so we're going to have r sub 2 is equal to negative 1. So we have for the complementary solution, we have y sub c of x is going to be equal to c sub 1 times e to the negative 3x. And we have plus c sub 2 times e to the negative x. Now for what we have on the right hand side, if we look at x times e to the 4x and negative 7, so again we have with x and e to the 4x. So if we draw out again from the family of derivatives, again we have with x and e to the 4x, again we have x, we have in the family of x to the n, we have like going from x to a constant, and e to the 4x is in the e to the ax family. And so we have for x, again we have x and 1, or you could just say x and a constant. So I'm just designating c for a constant. And for e to the 4x, so I have e to the 4x. Now, we have in the equation, we don't have just a standalone x or a standalone e to the 4x. Once again, I'm looking at x times e raised to the 4x. So looking at the interacting between what we have in the families of derivatives. So if we look at, in a sense, distributing, so you have x and c, which will be multiplying e to the 4x, and just putting in sort of diminutive terms, we have x times e to the 4x, and we have a constant times e to the 4x, and again, in diminutive terms, we have e raised to the 4x. And if you notice, we don't have any duplication of e to the negative 3x, nor do we have one of e to the negative x. And for what we have in the case of negative 7. Okay, well, in the case of negative 7, okay, that is just going to be a constant. And so in setting things up for y sub p, okay, again, we have xe to the 4x minus 7. And if we take what we have in the family of derivatives, okay, so we have from xe to the 4x, I have this family. Okay, so we have the elements at xe to the 4x and e to the 4x. And if you notice, we have the operation of subtraction separating xe to the 4x and minus 7. And in terms of what to do with the families of derivatives, you can take the operation of union. So we're looking at taking the union of xe to the 4x and e to the 4x with a constant. And so in terms of what we have with the family of derivatives, okay, so once we take the union, again, there's no repetition of elements. So you have xe to the 4x, e to the 4x, and we have a constant in general. And this would be the pathway to where we can utilize what is referred to as the method of undetermined coefficients. Now we have three distinct elements from taking the union of the families of derivatives. Okay, so we're going to have three distinct coefficients. We're going to have a in front of xe to the 4x, and we have plus b times e to the 4x, and we have plus a constant c. And now, if you notice, we have the equations going up to the second order derivative. So I'm going to take both a first order derivative and a second order derivative for y sub p. Okay, so if I work with axe to the 4x, what we have in the case of the product rule expansion, okay, so we have taken the derivative of e to the 4x times ax. So this is going to be 4ax e to the 4x. And if I take the derivative of the first term with respect to x, I'm going to have ae to the 4x. And guess what? If I take the derivative of be to the 4x, that's going to be 4be to the 4x. So I can do a little bit of consolidating, but I'm just going to do this later on. Okay, so we got, in this case, so we're going to have ae to the 4x plus 4be to the 4x and the derivative of the constant c is going to go out. And if I go up to the second order derivative, okay, so with respect to e to the 4x, we have 4e to the 4x times 4ax, so we're going to have a 16ax e to the 4x, and guess what? We're going to have taking the derivative with respect to x, we have 4a to the 4x, and guess what? And we have another 4a to the 4x, and just using a little bit of color coding, like I'm just going to use blue to indicate that we have combined like terms together. And then for what we have for 4be to the 4x, taking the first order derivative, so this is going to become 16be raised to the 4x. And just looking at what we have in the layout. Okay, so just taking what we have from the original equation, and if I put this in terms of where we have y projected to the particular. Okay, so we can have in the set, so we can say we have yp double prime plus 4 y sub p prime plus 3 times y sub p. Okay, continuing, we have just wanted to mention, okay, so you have y sub p double prime. You have 16ax e to the 4x. I think I forgot to write down the x, but it's going to be 16ax e to the 4x plus 8a e to the 4x plus 16b e to the 4x. And translating what we have in these expressions, okay, so we have y sub p double prime plus 4 times y sub p prime plus 3 times y sub p. And again, we have set equal to x times e to the 4x minus 7. And again, so if I combine like terms, so we have 35 axe to the 4x, and for what we have in just e to the 4x, we're going to have the quantity of 12a plus 35b times e to the 4x, and we have 3 times c is going to be the standalone constant term. Again, we have is equal to x times e to the 4x minus 7. And looking at what we have in terms of what can be mapped together. So you have an xe to the 4x, okay, you have 35a on the left, and you have to the right, the coefficient would be just 1. So we have that a is equal to 1/35, and we can just look at the correspondence between the constants. So you have 3c is equal to -7, so we have that c is equal to -7/3. Okay, and notice we don't have a standalone e to the 4x expression. Alright, so that means we would have 12a plus 35b is equal to 0. And so now we got a is at 1/35, so b is going to be non-negligible. Okay, so you have 12/35 plus 35b is equal to 0. And so for b, okay, if you have like 35b equal to -12/35, okay, this is kind of a brutal fraction where we have -12 over 1,225. So going back to what we have for the coefficients, okay, so for y sub p, okay, so the a, you have at 1/35. B we have at -12 over 1225. And again we have with C that will be -7/3. So you have y of x equal to the resulting terms we have for the particular as well as the complementary solution. And quite a long one in this case. Okay, now let's say if we're looking at this non-homogeneous equation, whereupon we have y double prime plus 9y is equal to the sum of the sine of 4x and the cosine of 4x. Now if we look for the complementary solution, okay, and again this would be if you had set up a homogeneous equation whereupon we have y double prime plus 9y is equal to 0, and translating what we have in terms of the characteristic root equation. So we have r squared plus 9 is equal to 0, and we have with r squared equal to negative 9. Again, we're back to the complex roots of positive and negative 3i, and just referencing what we had with the Euler equation. Okay, so we're going to have for the complementary solution, we're going to have sine and cosine terms that will have the coefficient in the angle to be matching the absolute value of what we have with the complex roots. Okay, and so we have for this one, so we have c sub 1 cosine of 3x plus c sub 2 times the sine of 3x. And looking at what we have with the terms on the right hand side. Okay, there's going to be a bit of redundancy. Now we got the sine of 4x, and for the family of derivatives we had the sine of 4x as well as the cosine of 4x. Okay, now we do have sine and cosine, but we don't have duplication of sine or cosine of 3x. And I'll mention also, okay, just with the cosine of 4x, again, you have a bit of duplication. Family of derivatives, again, you have cosine of 4x as well as the sine of 4x. Again, we have no duplication, and just setting things up for what we have in the particular. So if we look at it through the prism of working with the families of derivatives, okay, and notice between the sets, okay, we have identical elements. And again, we have the operation of addition between the sine and the cosine of 4x. And in terms of working with the families, okay, so addition or subtraction, once again, will translate to the operation of union, okay, between the families of derivatives. And if you notice, okay, we don't have any new elements to add to the first set, okay, because you have sine and cosine, you just have just kind of revolving, okay, and just have repetition. So for what we have in the family of derivatives, where we have just sine of 4x and the cosine of 4x, and again, anytime you have the elements to repeat, you just need to put them down only once. Okay. And so we got sine of 4x, cosine of 4x. So just setting things up, so we have y sub p, and we have initiating the method of undetermined coefficients. So we're going to have a sine of 4x plus b times the cosine of 4x. And just like earlier, we're going to take out to the second order derivative. Okay, first of all, I had to go through the first order derivative. So we're going to have for a cosine of 4x minus 4b sine of 4x And we have with y sub p double prime. So we're going to have negative 16a sine of 4x minus 16b cosine of 4x. And again, I'm going to take this equation and put it in terms of the particular. Okay, so taking the equation and putting it in terms of the particular solution, so you got y sub p double prime, which I have with negative 16a sine of 4x minus 16b cosine of 4x, and you have plus 9 times y sub p. So there's no y sub p prime involved, so we got 9 times a sine of 4x plus b cosine of 4x, and again we have equal to the sine of 4x plus the cosine of 4x. And so just combining like terms together, so you're going to have negative 7a sine of 4x and minus 16b cosine of 4x plus 9b cosine of 4x. So we have minus 7b cosine of 4x, and again we have is equal to the sine of 4x plus the cosine of 4x, and just matching up what we have here. Okay, so you got negative 7a is equal to 1, from which we're going to have that a is equal to negative 1/7, and negative 7b cosine of 4x equal to 1 cosine of 4x. b is likewise at negative 1/7. Okay, so for what we have, taking these coefficients, okay, so we have with y sub p, so we have, again, both a and b are at negative 1/7. Once again, we have with a and b at negative 1/7, so going back to the particular, again, we have negative 1/7 of the sine of 4x minus 1/7 of the cosine of 4x. And for the whole unabridged solution, we have, in the general case for y of x, you have combining the particular with the complementary, and so we have these 4 terms in the end result.